guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we move on to talk about the second trend, which is ionization energy. So conceptually, ionization energy is the opposite of electronegativity, but we'll discuss that in a second. So the definition of this energy is the energy required to remove an electron from an atom that's in a gas phase. So this means that the further away an electron is from the nucleus, the easier it is to remove. Let me explain to you what I mean by that. So let's look at this blue arrow right here. This shows that as you go down a group, ionization energy decreases. Why is that? Well, we just talked about atomic size, right? Where we said lithium has 3 electrons, and so it looks like so. And sodium, which is right below it, on the other hand, has 3 shells. And so this electron in the sodium outer shell is going to feel the pull of the nucleus a lot less than this electron, which is in closer proximity. And so the energy required to remove this electron and basically to overcome this positive and negative attraction is going to be greater for lithium versus the sodium. So this is called electron shielding, where basically there is a shield of electrons in the middle that is blocking the positive charge from being felt by the electron. So also when we go across the periods, ionization energy increases. So if you look at this little diagram right here that I popped up, you can see that the noble gases has the highest ionization energies. We have helium right here, neon right here, and argon. And so why do these have very high energies? Well, when you have a noble gas, it has a full outer shell. So this is a very stable conformation. When an electron has a full outer shell, it's stable, it's happy. So in order for us to remove this electron, it requires a ton of energy because helium wants to keep both its electrons. The same can be said for neon that has 2 in the inner shell and then 8 valence electrons. It wants to stay in this configuration, and thus to remove one of these electrons will require a lot more work than if we wanted to remove it from oxygen, for example. So removing the second electron is always harder. What that means is after I remove this electron from neon, the second electron is going to be harder to remove. So the second ionization energy of any element is always higher. So this is a really important concept. So let me do an example for you. Let's take aluminum. So aluminum has 13 electrons. So 2, 8, and 3 in the outermost shell. So aluminum can have various ionization energies. So the first ionization energy will be removing this electron. I'm going to write that as IE1. And let's say that's approximately 100 kilojoules per mole. I'm just making up these numbers, so don't quote me on this. And so the second electron removal is going to require more energy. So let's say it's going to be approximately 300 kilojoules per mole. Same could be said of the third electron. The ionization energy, this is 2. 3 is going to be higher. But then here's the big important part. The fourth ionization energy for aluminum is going to be drastically higher than any of these previous ionization energies because you're taking it from a shell that's closer to the nucleus. So as I mentioned about the shielding effect, the closer a shell is to the positively charged nucleus, the more pull it feels, the more attraction it feels. And so this fourth ionization energy, IE4, is going to be, let's say 4,000 kilojoules per mole. So this is actually a very good indicator of what kind of element we're looking at. If we see a very big jump between ionization energy 3 and 4, we're going to know, Okay, when I take out the fourth electron, I'm probably removing it from a different shell. So when you solve problems in trends in ionization energies, these are things to look out for. Where is the jump and how is it changing based on that specific element?